Hello, everyone, and thank you for your interest. In this talk, I'll be presenting the work we've been doing at Microsoft Research as part of Project STEMA. STEMA stands for Secure, Trustworthy, and Enhanced Memory for Azure. My name is Stefan Saroiu, and I'm a researcher in Microsoft Research. And for the past 6 years, together with my colleagues, we had front seats on all the work done on solving Rowhammer in both industry and academia. And as a result, we have a somewhat of a unique perspective on this whole space. Today, I would like to share with you some of that perspective. Now, as part of Microsoft Research, I sort of wear two hats. I'm an academic because part of our job is to push the state of the art in computer science. But at the same time, I'm in industry. I work for Microsoft, and I actually work on building more secure and more trustworthy systems for the company. So if I were to put my academic hat and looking back at Rowhammer, I would be puzzled by how industry has responded to this security threat. And this talk is meant to shed some light on that behavior, on how industry thinks, so academic researchers can better anticipate which Rowhammer-related problems will continue to matter in the future. At the same time, I spent a lot of time in the DRAM industry interacting with folks from companies that form this landscape. And what I learned is that folks in industry are also confused about what motivates academic researchers. And again, hopefully this talk will clarify the role of research work, its significant impact in the past, and its continued importance in the future. Now, as probably many of you know, security attacks by nation states are on the rise, and cloud systems have been frequent targets of such attacks for a couple of years now. Now, I have a small subset of headlines here that show a troubling reality, that despite the cloud industry's best efforts, some of these attacks have been successful at stealing data, such as email or files and so forth. And on this slide, I'm actually showing headlines that on security attack that breached Microsoft, but Microsoft is not the only company that was breached by these attacks. Pretty much all cloud systems have had problems with nation-state attacks. Now, this issue extends far beyond the security of our software systems. It directly threatens the core existence of the cloud and, more critically perhaps, the safety of national infrastructure. Nation-state attacks threaten not just cloud survival, but national security. Now, I would like to argue that we have not yet seen the worst. And the reason why we haven't seen the worst is because we haven't had to operate the cloud, at least in the Western world, we haven't had to operate the cloud during an open conflict. In a period of an open conflict, there is another goal that often surfaces, not just to steal email and files, but to actually disable critical infrastructure to cause widespread pain. So the question I want to pose is, how can a nation-state attack cripple cloud infrastructure? Now, imagine the following hypothetical scenario, and this is a scenario that actually keeps me up at night. Imagine one day we wake up to find that hundreds of thousands of cloud servers are endlessly rebooting, shutting down, or hanging. Such an event would mark a critical moment for the cloud, challenging the very foundation of trust and reliability that the cloud have really tried hard to build and maintain. And more importantly, the business is relying on cloud computing, such as, cloud computing, and whether it's AI, storage, compute, or whatever else it is there, they will face significant operational disruptions. So what might such an attack look like in practice? And what I'm going to do here, I'm going to give a simple two-step recipe on how such an attack can be mounted in practice by a nation-state attack. Imagine that the nation-state acquires knowledge of a hardware vulnerability that can crash a cloud server and that can be exploited with simple user-level access. So let's say they create a script, and I'm going to call that script rowhammer.sh. And the second step, they're going to acquire many VMs. VMs here stands for virtual machines in the cloud in different regions and data centers. And they're going to run this script all at once. Now, that will actually create a massive wave of server crashes rolling across the cloud infrastructure. And that would actually be an example of a recipe of the attack I'm just imagining and describing here. Now, Rowhammer is a DRAM security vulnerability and is a prime example of such an attack vector. It's a hardware vulnerability. Now, what is Rowhammer and why is it dangerous? Before I continue, I want to say that this is going to be the world's shortest primer on Rowhammer. If you want to understand how Rowhammer works, what causes it, and why it affects DRAM, and how DRAM works, there are a couple of really good tutorials on YouTube. Some of them you can search for my name, but there are others actually who have done a really good job of talking about Rowhammer, and I encourage you to watch them. But here I'm going to briefly explain what Rowhammer is, just so that the rest of the talk makes sense. Now, on this slide, you have a DIMM. A DIMM stands for a dual inline memory module. And it's basically how DRAM is organized in a server or in a desktop PC as well. So when you actually open up a server, what you see is a lot of these DIMMs side by side, and there are dozens of such DIMMs. And a DIMM is simply a printed circuit board or a PCB that holds multiple DRAM chips right here. So you can see DRAM chip one after another hold here on a DIMM. The DIMM has two sides, and on this slide you see the front side, but there is a back side as well that is almost identical. It has as many DRAM chips as the front side has. Now, if you zoom in a DRAM chip, you have billions of cells, so lots and lots and lots of cells. This is not, by the way, this is not a realistic picture. It's just sort of a picture to give a mental intuition of how cells look like. And these cells are organized in rows and columns, and there's a ton of them, billions of them. Now, Rowhammer corrupts memory. And the reason why that is because in DRAM, when you access a DRAM row, you disturb nearby DRAM rows. Now, when you read or write data inside of the DRAM, the way you do that is by accessing a DRAM row. That's how DRAM works. And when you do that, you basically disturb the contents of nearby rows. So here, row R, when I access it, I disturb the contents of row R-1 above it and R+1 below it. So the way Rowhammer works is I'm going to access row R at a high rate over and over and over and over again. These disturbances are going to accumulate. And what I'm going to see is I'm going to actually have enough disturbance that I'm going to affect row R-1 in this example. And I'm going to flip the bit in red there from 1 to 0. A little bit more terminology. Row R is called an aggressor row because I'm actually activating that row. I'm not flipping bits on row R, by the way, actually. I'm flipping bits on victim rows. Now, victim rows here are the adjacent rows, but I could have victim rows that are nearby, not necessarily adjacent. So here I have, I have two adjacent rows, row R-1 and R+1, but I could also affect rows R-2 and R+2, R-3 and R+3, and so on and so forth. Rowhammer is a physical effect, so the further away I go from the aggressor row, the less of an effect I have. So some row here far away from row R, it won't be affected by row R at all. So this effect will eventually be negligible and diminish and disappear. But the closer I am to aggressor row, the more affected I am going to be as a victim row. Now, what's bad about corrupt memory? Corrupt memory has two side effects. First, it can lead to security vulnerabilities. And there is many research papers out there that have shown how Rowhammer can be used to break into secure systems. And this makes sense because when you consider how software works, it assumes that memory is reliable. When a program reads a bit from memory, it expects to get back exactly what it wrote and not a corrupted value. And obviously, you can think about a password program. If the password program checks that if your password is, let's say, ABC123, that's the correct password, it's going to let you in. So if I flip that check and I'm going to check that if the password is not ABC123 and I'm going to let you in, I'm going to then exploit the system that way. And you can exploit any system you can imagine: browsers, operating systems, hypervisors, secure enclaves, anything you can imagine as a software system that relies on software, you can exploit with Rowhammer. Now, the second side effect that actually has been a lot less examined in academia is one where you corrupt memory and that leads to servers to actually shut down, reboot, or hang. And although it has been a lot less examined by academia, in practice, this is a much serious problem. The reason why it's a much serious problem is because mounting such an attack with Rowhammer has a lower bar. In the first example, in order to corrupt the system, I have to flip a particular bit that is critical to the security of the system. to cause a machine to hang, there's a lot more targets. There's a lot more bit flips that I can actually go and target. And if I flip a sufficient number of bits, it's fairly straightforward to actually cause a server to shut down. And it's a serious concern in practice. Now, on this slide, what you see is a graph that shows how looks at how whether newer DRAM is more susceptible to Rowhammer than older DRAM. And on the y-axis, you have this metric called the hammer count. Don't worry if you don't know what it means. I'm going to explain it. On the x-axis, you have process nodes. And we're looking at different process nodes, 1x, 1y, and 1z. Think of process nodes as basically different DRAM technologies. The DRAM manufacturers improve their technology, and these are the names for those technology, and they call them 1x, 1y, 1z, and 1y is a more recent technology than 1x, and 1z is a more recent technology than 1y. Don't worry if you don't know what it means. I'm going to translate this in English. So the metric on the y-axis is a metric that basically measures how resilient the memory to Rowhammer is. And on the x-axis, you have different DRAM technologies. And 2021 H2 means this technology appeared in the second half of 2021. The technology in the middle is the first half of 2022, and then the second half of 2022. For each date, we have 3 bars corresponding to 3 different DRAM vendors. About 95% of all the DRAM in the world is manufactured by 3 DRAM vendors, and these are Micron, Samsung, and Hynix, and the A, B, and C correspond to these 3 companies, but I'm obfuscating which one is which. Before I go and talk about the graph, I do want to say that we've disabled all the in-DRAM internal mitigations, and I'm going to talk more later about this, but this measures basically how resilient the actual DRAM cells are to Rowhammer. And what you can clearly see is that this resiliency drops over time. So newer DRAM is in fact worse than older DRAM with respect to the actual underlying medium. And it makes sense why that is, because newer DRAM actually, as all hardware manufacturers want to do, they want to shrink their lithography. They want to make things smaller and smaller and smaller. And as I explained how DRAM is a physical effect, as you shrink cells and you make things smaller, you're going to exacerbate the Rowhammer problem. Things are going to be more near each other, and that's bad. So the bottom line is that DRAM is unreliable, and the Rowhammer risk makes DRAM vulnerable to whether security attacks or reliability attacks, where you crash a lot of servers that ultimately lead to nation-state attacks, like the ones I've been describing. Okay, so that concludes the background and the motivation for my talk. In this talk, I have 3 takeaway messages. So if there's something that I want you to leave with, they are the following 3 takeaway messages. First is that researchers have helped keep industry honest, and this is a tremendous impact that they had, and I'm going to describe why that is. The second thing is that the lesson, and this might not make a lot of sense right now, but it's going to make a lot more sense as I go through my talk, is that to have impact as a researcher and also as an engineer, you have to work together with a lot of different participants in the industry. You have to work together with the industry and not against it. Typically, a lot of security researchers out there, like to sort of demonstrate all sorts of problems and show how different things don't work very well, and that's healthy. And that covers the first message. But if you really want to make a change and make things better, you have to work together with the industry. That's the lesson we've learned in this work. And the third problem is, and I'm going to show you how today we have much better tools to actually address the Rowhammer problem, nevertheless, than ever before. Nevertheless, Rowhammer is far from being a solved problem in industry. This slide is very busy. It shows a timeline of Project STEMA from 2018 to 2024. And it's really not meant to be read. I'm going to use this to sort of as an outline for the rest of my talk, as I'm going to go year by year and explain why we've done the work we've done. I'm also not going to talk about all the work. I'm going to pick and choose the ones that are the pieces of work that are most important and more relevant. So we started in 2018, 2019, and at the time, with Project STEMA, the attitude in industry was, oh, Rowhammer, yeah, who cares about this problem? So let me explain why that is. in 2018, 2019, there were several papers in academia written by academic researchers that show that DDR3 suffers from Rowhammer. Now, what's DDR3? DDR refers to the type of DRAM that actually servers used, not just servers, but most servers use DDR. And at the time, DDR, at the time in 2018 and so forth, the memory that new servers would come equipped with was DDR4. So at the time, the DRAM vendors basically said, well, these papers show that DDR3 is affected by Rowhammer, but now we actually are shipping DDR4, and DDR4 is safe. By the way, just to be clear, if you buy a server today in 2025, the memory that often it comes with is DDR5. DDR4 is now considered somewhat obsolete. So, I went around. I didn't know a lot about Rowhammer. I didn't know a lot about DRAM in 2018. I went around in industry, in Microsoft, and I said, hey, do we care about this problem, Rowhammer? And the attitude was, well, we don't really care because DRAM vendors have given us assurances that DDR4 is safe. And indeed, if you go online at the time and read about DDR4, you would see a lot of claims that were pretty strong, like this particular guy who was an expert on semiconductors used fairly strong language, like DDR4 eliminates Rowhammer. But the DRAM vendors also made statements like DDR4 is Rowhammer free, which is a very strong statement. And this statement is a little bit weaker. DDR4 devices perform TR mode in background. What this means, at the time, it was very unclear what this means. But basically, it says we have a mode that fixes Rowhammer. We're going to run that in the background. And that was true. The thing that wasn't true was that it doesn't really fix Rowhammer. It fixes a small portion of the problem. So in 2020, the academic community, there was a breakthrough that led to a change in this attitude. And that was actually a paper that was published at IEEE Security and Privacy in 2020. This conference is known in the academic circles as Oakland. The name of the paper is Trespass, and the paper was published by a research group at ETH in Zurich. And again, this is a fairly busy slide. What I'm going to do, rather than go over it, I'm going to extract some numbers, and I'm going to present them in a table that's easier to read. So these are the same numbers. It's a sample of the table you've seen before. Now, what you see on this table is that what they've actually been able to do is flip bits using Rowhammer. And at the time, for the time being, these were modern DDR4 DIMMs. So you see here, these two first digits mean that the year when this DIMM was manufactured. So was this in 2019. So this paper was published in 2020. So this was a fairly modern DIMM for the time, 2019. Probably the work was done in 2019 as well, and some older chips as well. But there were more modern DRAM, DDR4 DIMMs for the time. Now, the way they were flipping bits is to use sophisticated patterns. And you see here 9-sided, 10-sided, 19-sided. What this means is that, until then, in DDR3 with the older work, people were using one aggressor row or two aggressor rows. And two aggressor rows were referred as double-sided. So what the idea is you target a victim row, and you're going to have two adjacent aggressor rows that basically sandwich the victim row, one above and one below, and that was a two-sided attack. And in this paper, they show that the way to flip bits was using more sided attacks, 3-sided, 9-sided, and even 19-sided, lots and lots of aggressor rows. And they show that they were able to flip a lot of bits, and that's bad because when you flip a lot of bits, you corrupt a lot of memory. And like I was telling you, we were particularly concerned about corrupting memory. So things were pretty bad. And one more thing, the same research group 2 years later, the same conference, SMP, but in 2022, they had time to hone their tools, and now they show that they were able to flip bits on pretty much any DDR4 DRAM chip they tested. Just to be, I want to say one more thing. Between 2020 and 2022, if you see here, not all the vendors were affected in the same. One vendor seemed a lot worse than the others, and one of the vendors actually started claiming, they are not that affected by this problem. And again, that was not true. So there was a particular history of claims made that were ended by industry that ended up being debunked. So it kind of led to a little bit of an untrusted kind of feeling in industry. So anyway, I have a funny slide here. This turned out to be fake news. At the time, this slide was kind of cool because that's when the term fake news was being coined. So I hope I demonstrated that researchers have had a tremendous impact, and in particular, what the impact has been is that it helped keep the industry honest. So it was a lot more clarity that DDR4 in fact was not Rowhammer free, and we have a lot of problems on our hands. So going back to Project STEMA, I went around asking people in Microsoft and in the industry at large, saying, well, we thought that DDR4 is safe. Look, clearly that's not the case. And the next thing we basically heard was, well, yes, but don't worry about it, or Microsoft should not be worried about it, because Microsoft actually receives from the DRAM vendors what's called server-grade DIMMs, and what the researchers used were client-grade DIMMs. And you might wonder, what's a server-grade DIMM and what's a client-grade DIMM? And it's a great question, and unfortunately, I don't understand what the distinction is. Presumably it has to do with something about testing, but I cannot articulate. I never really understood what the difference between server-grade DIMMs and client-grade DIMMs are. But we shouldn't be worried about, because the academics use client-grade and Microsoft uses server-grade, and we're safe. Okay, so that was sort of the time when we started Project STEMA. And the first thing we did in Project STEMA was to build a state-of-the-art software and hardware DRAM lab at Microsoft Research. And I can give a talk about our lab, but what I'm going to do here is I'm going to show a couple of photos. And at the bottom, what you see is different Azure blades that we actually went and took from the data center and put into our lab, and we opened them up. And there are different generations. Every couple of years or so, Azure builds a new architecture of their blades, and these are 3 different generations. The one on the left here at the bottom was the most modern one for the time being. But the other thing we actually did was we went and purchased a bus analyzer, and I'm going to talk about it. And this allowed us to basically gather traces of DRAM, the commands that DRAM actually receives. And we also build all sorts of fault injectors, and I'm going to talk about them. So what we did with our hardware, we started replicating the work from Trespass and Blacksmith. And we used server-grade DIMMs. And what we did was we started mounting similar sort of patterns. And guess what? We flipped bits. And in this slide, as you can see, we flipped a moderate number of bits. But the reason why we flipped a moderate number of bits was because we didn't try too hard. Our goal was to see whether these things actually also work on server grades. So yeah, mission accomplished. They do work on server grades. We can flip bits. So what we actually did around 2019, 2020 was to basically establish an industry that server-grade DIMMs are also susceptible to Rowhammer for DDR4. So this assurance from the DRAM industry was debunked again. We're not safe. The next thing was, so again, we did the same thing. We went to talk to people in industry, and what we heard was, well, yes, but Microsoft should not be worried about, or at least the cloud should not be worried about, other cloud vendors, because crafting an attack from a virtual machine is extremely difficult. And the reason why, and there were terms used like impossible. The reason why it's difficult was one of the first reason was that, as you can see, when you mount Rowhammer, you have to worry about adjacent rows, right? You have to have aggressor rows that are adjacent to victim rows, and you have to understand how the geometry of a DRAM is. And when you run code in a virtual machine, you deal with cache lines in a virtual machine with guest physical addresses or some sort of virtualized addresses, and mapping those to actually adjacent DIMMs in a DRAM, adjacent DRAM rows in a DIMM is impossible. And we said, oh, yeah, okay, let's figure that out. And what this graph shows is that the different mapping layers, and there are many, these actually talks about the high level 4 mapping layers, but there could be significant other complications. But I'm not going to talk about virtualization. I'm going to assume that you just have a hypervisor with an OS, or maybe an OS with a process. So the first address mappings that you have to reverse engineer to mount an attack is virtual to physical. And in general, these are assumed by security researchers as pretty straightforward to reverse engineer. I list some papers that talk about how to do that down there, but I'm not going to talk more about it. This in general is assumed not to be a particularly difficult task. But the next task is to map physical addresses to what's called DRAM control addresses, or maybe media access, that's another, or DDR addresses, those are other terms. And, there is not public documentation of how to do this very well, and it's specific to the motherboard and to the BIOS settings. About a lot of other things. There is a paper in 2016 that showed an interesting way to do that. But it's not particularly. It was particularly actually laborious to do that. So to do these things, it was like, how are we going to do these things? So what we've done was we've basically bought a secret weapon, and what that is a DDR bus monitor. So let me explain what that is. So again, going back to the problem, what you want to do here on this slide is you want to map what I'm going to call a system physical address. So you can think of this as the memory controller receiving instructions from the CPU. MC here stands for memory controller. Let's say load a cache line from this particular address. And the memory controller translates this address to the following bus address. And this says, I want to access row 0 in a bank group 1, in bank 0 in row 74. Don't worry what this really means. It basically means a particular row in this device, right? So I have many devices like that, and they use terms like ramps to partition the devices, banks and rows, and so on and so forth. So I need to map, and the memory controller maps these two things. So the secret weapon was to buy this bus analyzer, like I talked about, and let me tell you what does bus analyzer do. It basically sits here on the bus and is able to actually see all the commands. Let me go back for a second. All the commands actually going on this bus, and in particular, those commands have those addresses. So we can now really easily reverse engineer, which addresses here map to which addresses in the DRAM. Let me show you a couple of pictures. This is a bus analyzer we purchased. It's from a company called Future Plus, which is on the East Coast. They build all sorts of tools like that and sell them. How expensive is this? I'm not going to talk about. I'm not going to quote an exact figure. It's not cheap. It's definitely not inexpensive, but it's not. We're not talking about millions of dollars or hundreds of thousands of dollars. Think of it on the order of, if you are an academic, think of it on the order of paying for a single graduate student for a year, or something like that. It's clearly within the budget of a nation state. This is not expensive for budgets like that. Now, when you use a bus analyzer, you get a trace. That's how a trace looks like. Maybe this is a little hard to read, so I'm going to zoom in here. And this trace basically has DRAM commands like read, pre-charge, and activate here. These are two ranks, rank 0 and rank 1. You can see some commands on rank 1 as well. And then you can see row addresses and bank addresses here, bank groups, and right here, and the time and column addresses, and so it's pretty straightforward to actually reverse engineer these maps. This is a map that we reverse engineer pretty straightforward from a major CPU vendor that Azure uses and the whole world uses. So we're able to reverse engineer these maps. Not a big deal. Now, the last set of maps I want to talk about here is on the right-hand side, and those are the maps from the actual memory, these bus addresses, these media addresses, to the actually internal to the DRAM. So, for example, I was talking earlier about row 0, row 1, row 2, and so on. That's what the bus addresses are. That's what the bus addresses use. But it doesn't mean that row 0 and row 1 are adjacent to each other. The DRAM can actually scramble those rows. The DRAM will continue to work just fine, even if row 0 and row 1 are not adjacent. There is nothing that says that they have to be adjacent. So how are we going to reverse engineer adjacency inside of the actual DRAM? So what we've done here is we borrowed some methodology from previous work, and I mentioned here on the rock on the right-hand side. But basically, the observation is that if you're able to hammer at a high rate and flip a lot of bits, the way that those bits actually flip will reveal internal methodology. So imagine for a second that internal internal mapping. Imagine this internal mapping is straightforward, and I'm hammering row K. So I hammer row K a lot, so I flip a ton of bits. Well, if you look at where the bits are, you're going to see a lot of bits flipped on k-1 and k+1. And then you're going to see fewer bits flipped on k-2 and k+2, and so on and so forth. So by measuring this density of how many bits you flip, you're able to reverse engineer what's adjacent and what's further away. And if you keep doing that, you can reverse engineer the adjacency inside of the actual device. Now, to do this, what you need to do is you need to have a DRAM part that flips a ton of bits. And some DRAM parts actually, as you can see, flip a lot of bits, but not to the extent actually that really reveals this kind of internal adjacency. So we need a way to flip a ton of bits. The reason why they don't flip a lot of bits is because inside of the DRAM, basically there is an anti-Rowhammer circuitry that actually prevents it from flipping a lot of bits. And the way to do this is to use a fault injector that suppresses DRAM refreshes. And you might wonder, well, what is the relationship between the two? So let me shed a little bit of light. So to make DIMMs always succumb to Rowhammer, we have to rely on two observations. The first observation is that we have to disable in-DRAM TRR, or target row refresh. Don't worry what this means. Think of these as inside Rowhammer mitigations. All DRAM today, well, I don't know if all DRAM, but I suspect all DRAM today, and in my experience, all DRAM, although I haven't seen DRAM that doesn't have Rowhammer circuitry in the form of this TRR. So the reason why DDR4 vendors were a lot more confident that they were safe was they designed this Rowhammer mitigation to stop the attacks that we have seen in the previous era in DDR3, where we were using one or two rows, single-sided, a single aggressor row, or a double-sided, two aggressor rows. But they succumb when you use multiple aggressor rows. They make the attack harder to mount, but it doesn't eliminate the attack. So in order to flip a lot of cells, we have to find a way to disable these mitigations. And suppressing refresh commands, in fact, disable these mitigations. I'm not going to explain why the connection. You have to trust me on my word here that if you do that, if you disable refresh commands, if you suppress refresh commands, you disable TRR. Refresh commands are commands that the memory controller sets periodically to the DIMM. So we want to suppress those. So we need to find a way to do that. So what we've done is we've built a fault injector to suppress refresh commands. And what does a fault injector do? Now, our fault injector, what you'd want in some sense is for the fault injector, in some sense, from a software principles point of view, you could imagine the fault injector looking at each command and saying, oh, is this a refresh? No, it's not. I'm not going to suppress it. I'm going to let it through. Or it's a refresh. I'm going to suppress it. Now, you can't do that. DRAM buses run at super fast speeds. To build something like that will be very, very expensive, and you'll probably need a serious engineering team to do that. So instead, with a fault injector, what we're able to do is to drive a signal to a particular value all the time. So what we want is our trick is we're going to suppress a signal, and we're going to always make it low or high. And because we do that, we're going to scramble certain commands, and we're going to make certain commands be undecipherable. And what we would like to do is to just refresh undecipherable. So here in this slide, you see a table of commands on the left-hand side here. So here you see the commands in DDR4. The refresh command is right here. Precharge commands, read commands, activate the row commands, deselect commands. And what you see here is different signals. And what this table says, if these signals are low or high, that's an encoded to a particular command. So for refresh, this signal has to be low, this signal has to be high, this is low, and this is high. So what we want is we want to take one of these signals and scramble it, change it, so that we mess up the refresh command. So we start looking what we're going to do. We're going to look at the signals one by one for refresh. So the first signal we looked at was low. So we can build a fault injection that always changes this signal. The chip select is called, or CS. Don't worry about this for a second. It's always going to drive it to high. And if we do that, we mess up refresh. Awesome. So that's great. Now, the reason why I put this thing here, this says deselect. So what this means is because this is now high, this refresh command is going to arrive to the DRAM as a high here, and the DRAM thinks this is a deselect command. A deselect command is a no operation command. So this is great so far, because what it means is the DRAM, the CPU sends or the memory controller sends a refresh command. We change it to a high, to a deselect command. The DRAM looks at deselect and says, I don't care about deselect, I'm going to drop it. That's great. The problem, unfortunately, is we are not going to just scramble refresh. We're going to scramble all commands that actually use this signal to low. So in particular, we scramble all of them. So when that fault injector is going to suppress all commands, they're going to turn every single command into a deselect command. We don't want that because we want to suppress refreshes, but we want to mount Rowhammer. So we want to be able to activate rows and read or write for them and pre-charge them and so on and so forth. And this messes up all commands. That's not a good signal to mess with. Okay, so we're not going to mess up with this low signal. Let's keep going. The next signal is this signal here. Now, if we change this signal, we're going to change this into a low. So now we have two lows here. So this refresh now is going to be interpreted by the DRAM as an activate. And we don't want to do that because we don't want to start activating God knows what rows. We mess things up. That's not a good signal to actually change. And by the way, we're going to turn all the rows, all these other commands into activates. Oh, that's crazy. Let's not do that. That's not a good signal. So we kept looking at the signals, and we found this A14 signal. Now, if you change this from a high to a low, this refresh command becomes similar to a mode register command. Don't worry about what these commands are, but in our case, this mode register command was ignored by the DRAM. I'm going to skip over some details. Read the paper if you want to get a lot more details, or shoot me an email. I'm happy to talk to you about it. So that's great. Now, what other commands are we going to mess up? We're not going to mess up these commands, but we're going to mess up these three commands. This command is an unassigned command. Okay, no big deal. We messed that up. No big deal. We don't care. Unfortunately, we're going to mess up read. Reads are going to become writes. That's a problem. But what we've done is, all we need is small Rowhammer. So what we're able to do is, we are going to mount Rowhammer using write commands. So not load instruction, but store instructions. And that's okay. And we're going to refrain from sending reads. So we can work with this. Yeah, it's a problem, but we can work with this. And we're going to mess up this other command, which is no operation command. That's it. So we only mess up reads, which is a problem, but that's okay. We can still mount Rowhammer attacks, which is what we want. So mission accomplished in some sense. This is the first fault injector we built, and it's called A14 fault injector version 1.0. The reason why now why it's called A14, because we messed up the A14 signal, and which was this particular signal here. And the way it worked is it had a button. So if you press this button, we would suppress by hand. We had actually, it was one of the students, Lucian Kozhokar, who built this, and he was actually pressing this button, and then you'd suppress A14 commands. Then he built something a little bit more sophisticated, and which had 3 more additional switches. And I'm gonna briefly mention what this is for those of you who are interested. When you mess that signal, the command gets scrambled. So if you actually have a command parity, a system that uses checks for the parity of commands, basically the DRAM is going to receive scrambled commands and is not going to pass the CRC checks, and it's going to raise alert. So what we did here with the 3 extra switches was to effectively disable alerts, so that the DRAM will raise alert, but the chip would actually the CPU will not, the memory controller will not receive this alert. We'll basically scramble it on the other path, on the receiving end. So this is a picture of the hook setup we used. At the bottom, you see the fault injector with the button. Here you see the bus analyzer, and here you see the DIMM. So we could check that when we would not press the button, the bus analyzer would see a whole bunch of refresh commands being sent, and we would press the button, the refresh commands would be turned into mark commands, and we were able to check that. So that's how we verified our fault injector worked. And using it, we discovered actually that, yes, rows are not in fact adjacent the way you think they are. So these row 0B here, it's fully adjacent with row 0A and row 0C. But if you look at row 0F would have half adjacency. row 0F would be fully adjacent to row 0E, but it will be only half adjacent to the row below it, 1, 0. The other half adjacent would be all the way to the 0, 0 here. So those will be what we call half rows. So using that tool, we are now able to reverse engineer the entire maps, and we develop a Rowhammer testing methodology for Microsoft and for other cloud providers who, we published a paper and we sort of describe, we open source the fault injector. This paper was published also in 2020 at the same Oakland Security and Privacy Conference that the trespass paper was published. So, going back, let's go back to the story. The story was, crafting an attack from VM is extremely difficult, if not outright impossible, because identifying physical adjacent route is very challenging. And, it's not. Look, a nation state can go do this, reverse engineer the entire address maps of a particular server, and then scale that up and mount it across all the servers that have that architecture in a data center. And the next thing then we heard from the DRAM industry, yes, but the problem we haven't yet solved was ECC, error detection and correction. ECC stands for error correction codes. This is a technique that all servers in Azure use, and I'm sure a lot of the cloud servers out there use. And it's basically designed to deal with DRAM errors. ECC has not been designed to stop Rowhammer. ECC has been designed to stop just transient DRAM bit flips, which happen perhaps due to cosmic rays or perhaps due to other errors in the DRAM. But ECC is quite powerful in DRAM, and it will actually eliminate Rowhammer. So the next thing we heard was, yes, you've done all this work, but you haven't really bypassed ECC, and that's going to stop Rowhammer. So at this point, I remember very clearly that we were actually going to embark, and we spent time thinking about how to bypass ECC using Rowhammer attacks and how to demonstrate that ECC won't stop Rowhammer. There is a paper published by the same group that published Trespass with Lucian. I talked about him earlier, that he built a fault injector in our group. He worked with these academics first, and then he moved to our lab to finish a postdoc. And when he worked with the academic group, he actually published a paper showing how to mount Rowhammer on a particular type of motherboards and memory controller that used a form of ECC, using Hamming codes, but it was not what's deemed in industry parlor a chip kill ECC. And when I was pointing out that paper to the industry partners at Microsoft, they pointed out that, but they're not using chip kill ECC, and chip kill will stop these things. So we're now thinking about going to work on showing that you can actually bypass chip kill ECC as well. And by the way, I don't know. I anticipate to see work showing that you can bypass chip kill ECC. We haven't done that work because I had an epiphany at the time that we've been working for a number of years. This is a lot of work. It's a lot of tedious work, and we've identified the following common theme: that whenever we actually demonstrated that one of their claims is in fact wrong, they would immediately shift the goalposts. Like, that was wrong, but there is a new claim now, and this claim actually has a ton of, another 6 to 9 months of other work, and you haven't shown that. So I've decided, let's not play this game anymore. It's not really productive for us. So now I'm shifting to the second part of my talk, where I want to talk about how impact comes from working with industry and not against it. And what we've done here, we started thinking, why is the DRAM industry slow to actually fix this problem? What's going on? So let's try to understand their pain points. So like I said, all DRAM has anti-Rowhammer circuitry. Now, I know this slide makes this strong claim, all DRAM. I don't know, maybe I'm wrong. I cannot prove that all DRAM, but all DRAM that I am aware of on DDR4, at least the ones that Microsoft uses, has some sort of anti-Rowhammer circuitry. And I'm going to show you some work that later on that we've done on cache coherence that kind of indicates that it must have anti-Rowhammer circuitry. I'm going to talk about that. Now, the DDR4 anti-Rowhammer circuitry has two significant limitations. What it does is it's basically built on tracking row accesses. It tries to actually identify when a row becomes an aggressor row. It's hot. There's a lot of activates. It's activated a lot. And it uses counters to count accesses to rows. But I was telling you, inside of a DRAM chip, there is a ton of rows. And the number of counters they can build, because they build these counters on circuitry or on SRAM sort of external to the DRAM, it's small. Maybe they can build, maybe let's say hundreds of counters or, something like that. But inside of a chip, you have millions of rows. Remember, I was telling you that inside of a chip, you have billions of cells, and those cells are organized in millions of rows. So no matter how clever you are, you're just not going to be able to track everything. You'll be bound to be imperfect. There's nothing you can do about that. You just don't have enough counters. But the second problem, which is a problem a little bit less studied, is that even if the DRAM identifies a row becoming hot, the DRAM needs to actually go perform work to undo the Rowhammer effect, to undo the disturbance effects. And there is really no good opportunity for the DRAM to do that, because the DRAM really typically is not designed to interrupt normal operation. The way DRAM systems work is the memory controller sends commands, and then it waits a specific amount of time for each command, and then it sends a new command. And the DRAM just basically obeys and executes those commands. The DRAM doesn't say, wait, hold on a second, I need to go do some other work that you don't need to know about it. I need to go refresh some victim rows. And there's really no good way to do that. What the DRAM anti-Rowhammer circuitry does, it tries to scavenge time from existing commands. So for example, if it receives a refresh command, it says, I receive a refresh command, but I don't need to go refresh because I'm doing a pretty good job keeping up with the refreshes in my internal circuitry. So I'm going to go do some anti-Rowhammer work during that time. Now, these two limitations that make DRAM ineffective at fully preventing Rowhammer attacks. So instead, what we've done is, at Microsoft, we developed Panopticon, which is a complete in-DRAM mitigations. And Panopticon is a very, very simple scheme. It has two main ideas. The first idea is, since we cannot build SRAM, we cannot have built circuitry to count all the rows because there's a ton of rows. And by the way, newer DRAM has even more rows than older DRAM. Let's actually implement counters using DRAM cells. And let's implement a counter for each row. So that then each row comes with its own counter, and that counter counts the number of accesses. And the second thing with it, I talked about this alert earlier, it's a signal used to, and it's a signal that is seldomly used by the DRAM to signal command errors. When the DRAM receives a command that it cannot decipher, the DRAM often raises alert and it says to the CPU, look, can you resend that command? It's a fairly coarse-grained command, but what Panopticon said, rather than flipping bits, if the DRAM doesn't have time to do work to undo Rowhammer, please do raise alert. The DRAM, the system will rather receive an alert than actually receive corrupted DRAM, corrupted bits. And Panopticon at the time basically also took a stance on how to build these counters in DRAM by building counter mats in a staggered pattern here on the right and left, as you can see, next to the data storing mats. But, for us, it was, we were agnostic where how you build these counter mats as long as the DRAM vendors basically reserve some portion of the mats to build counters. And then we had incrementers here. So we just wanted to see this idea in their heads. They are probably the best equipped to actually figure out how to build this most efficiently. And there was a lot of hum and ho about, we don't, building counters is going to increase the size of our dies by a huge fraction, 10%, 12%. And they kept at it. And we kind of kept talking to them. And those numbers are much, much lower today. So we had this idea in late 2020. We published a paper in 2021. I want to give credit to Tanj Bennett. He's the person who one not very well kept secret about myself is that I'm not the hardware guy. I cannot build hardware. I have to rely on people who understand hardware, Lucian and Tanj, to help me. And Tanj was the hardware engineer at Microsoft who came up with this idea, and we just sort of work with him to sort of adopt it and make sure we fix Rowhammer. We built a reference implementation or a simulator of Panopticon. It's open source on GitHub. There is a simulator here. It's written in Julia. It's done in a Jupyter environment you can actually play with. So you can change things and run. It's very, very nice. So what we have done since 2021, we've relentlessly worked with the DRAM industry to adopt Panopticon in whatever shape or form. What we want is those two things. We want per row counters, and we want to never see bit flips, but to see alerts if you cannot find time to fix things. And there's a lot of other corner cases that I'm not going to talk about it that we've worked together with industry to adopt them at JDEC. JDEC is the consortium that actually adopts DRAM specifications. So during this era, we built Panopticon. We also built MFIT. This is work done by Lucian, which is a programmable fault injector for DRAM commands. You can do cute things like this, where you can actually run code while you're suppressing refreshes. This is the fault injector. He got rid of the kind of silly button, and he instead used a controller here with a breadboard to actually programmatically press that button or sort of simulate the pressing of the button using electrical signal much faster than the human, but still not as fast as the DRAM bus. So it's a much coarser grained bus than the actual DRAM bus. So it's still much slower than the actual DRAM bus. But he had a lot of fun building that thing, and it was kind of interesting. We've done some studies with it. While we were working with the DRAM industry to adopt Panopticon, we continued to improve the state-of-the-art of Rowhammer defenses. We worked with the rest of the industry to release the DDR5 DRFM specification. DRFM stands for Directed Refresh Management, and it is a new DDR5 command. This command enables Rowhammer defenses inside the memory controller, not just in DRAM like Panopticon, but in the memory controller of the host. There are many proposals in academia to defend against Rowhammer, and all these proposals require a new command. Some of these proposals refer to this command as neighbor row refresh, others as adjacent row refresh. The DDR5 DRFM specification calls this new command DRFM, and the command is similar to both neighbor and adjacent row refresh. However, for now, I'll be presenting Moesi Prime, which is a paper we published that shows how commodity workloads, so the workloads that you run typically in the cloud, such as Memcached or virtual machines, can easily hammer DRAM accidentally. This is a very important observation. While everyone thinks of adversaries that craft careful hammering patterns to mount Rowhammer attacks, this paper shows that it is possible or even likely for simple, normal, commodity workloads to hammer memory. I will explain why that is. So to explain these results, I need to present cache coherency in Intel servers. Cache coherency ensures that multiple caches in a system maintain a consistent view of shared data. In this figure, you see two sockets, a local socket on the left and a remote socket on the right. Each socket has many cores. I only showed two here, but sockets have many cores. And each core has L1 and L2 caches, and they share a last level LLC cache here. When one socket modifies a cache entry, all other copies of the cache entry, especially those present on the other socket, are no longer valid. They're stale. And we would want to prevent the other socket from using these stale copies. For that, the socket modifying the cache entry needs to inform the other socket that the cache entry is modified and all the copies are now stale. And this is done through broadcast. So the way that works is whenever a socket or a core on the socket modifies a cache entry, it shows to everyone, this cache entry has been modified. And if you have copies of this entry, mark them as stale, please. Now, broadcast has one great advantage and one great disadvantage as a protocol. The advantage is that it's super simple. The disadvantage is that it doesn't scale very well. It's great at small scales, but it's terrible at large scales. For servers with lots of sockets and cores, it becomes a bottleneck. The scalability limitations of broadcast protocols has made Intel abandon them in newer server post-2016. Starting with the Skylake line of servers, cache coherency is no longer done with broadcast, but with directory protocols. The idea is that each cache line has, let's say, 1 bit. In fact, it has a small number of bits, but in my example, I'm going to use 1 bit that indicates which socket owns the cache line. For example, if the bit is 0, that means the local socket owns the cache line, and if the bit is 1, the remote socket owns the cache line. So if the remote socket wants to modify the cache line, it needs to set this bit to 1. And rather than broadcasting it, cache coherency is done by modifying this single bit, which is in fact stored in DRAM. So what this means is that each change in the ownership of the cache line leads to a DRAM access. So if cache lines ownerships change frequently, DRAM ends up being hammered. How can cache lines change ownership frequently? That's pretty simple. Imagine a multi-threaded application where its threads execute on multiple sockets. This graph shows the hammering rate on the y-axis for two workloads, Memcached and TerraSort. And these are two common workloads found in the cloud. The blue bar shows the hammering rate, how many accesses these workloads make to memory when their threads are scheduled across sockets. The orange bar shows the hammering rate when the threads are all confined to a single socket. When they are confined to a single socket, the DRAM accesses are at a low rate because we only have to use DRAM accesses to update states. But when the threads actually are scheduled across sockets, then the hammering rate is much, much higher. And that's because of the cache coherency protocol where threads actually have to share data. Often the data they share is locks, and that sharing of the data leads to a high rate of hammering. So commodity workloads can now hammer DRAM. Now, to summarize, the contributions of this paper were twofold. We show that commodity workloads can hammer DRAM when scheduled across sockets. But second, we also made a modification to Intel's MoESI protocol to reduce these hammering rates. And I encourage you to read the paper for more details. Now, going back, when we went back to industry, we now have even more reason to go and fix Rowhammer for DRAM. This timeline on the left now shows how we not only did MoESI Prime, but we also worked on doing a really thorough job on explaining and deriving the formulas on how to configure another class of Rowhammer defenses present in the host that are based on row sampling. For those of you working on Rowhammer, these defenses are typically referred to as para. And we actually wrote an entire paper on how to configure para properly. There is also a presentation online on YouTube at this address where you can listen and understand sort of how we derive that configuration and use it for your own needs. Okay. In 2022, 2023, we're still working with industry to adopt Panopticon. We worked on two things. We worked on silos. Silos is leveraging DRAM isolation domains to prevent inter-VM Rowhammer. And appear at SOSP, which is another conference. That's a lot of words. I'm going to give you the high-level bit of what this Silos paper does. I think it's very, very nice. It's an academic work. We have not been able to use this in production. But I was telling you that DRAM today stores cache lines. And today, DRAM is interleaved and all these cache lines are interleaved. And what that means is that basically the DRAM, if you were to open it and look at cache lines and color them, you'd see, like a rainbow like this. So the cache lines from a virtual machine or from a tenant are physically adjacent to the cache lines belonging to another tenant. Everybody's near each other in DRAM. So it's sort of interesting, if you look at the cloud architectures, cloud actually tries to partition very strongly tenants. They would like to partition virtual machines. Well, VM A is given to tenant A, VM B is given to tenant B. Maybe this CPU is given and this cores are given to tenant A and this cores to tenant B, so we don't have speculative execution attacks like Spectre and Meltdown. But in DRAM, everybody's near everybody else, and that's actually kind of concerning, and especially if you start thinking about Rowhammer. So Silos basically came up with a software-only way to do strong partitioning inside DRAM, where a tenant cache lines are partitioned, they're isolated from cache lines belonging to another tenant, to another VM. That's all I'm going to talk about this paper. Go read the paper if you are interested. The other thing that we worked on that I'm not going to talk about is we worked inside Microsoft on a project that to this date secret. Hopefully it's going to become public pretty soon. on building a silicon-based Rowhammer defense that is, in my opinion, state-of-the-art. Not as good as Panopticon. Panopticon is still superior, but in the meantime, while Panopticon is still just being adopted, this is, in my opinion, state-of-the-art in industry. In 2023-2024, finally, JEDEC in DDR5 released PRAC, or now the people use the term PRAC. I'm going to start using that term too, specification. And PRAC, and this is the announcements online from JEDEC on releasing PRAC. It was released in 2024. You can read what these things are, and it's extremely difficult to understand for anyone who has not been at JEDEC. Unfortunately, JEDEC still has a long way to go to actually make these sort of communications a lot more clear. But if you read them, basically, I'm going to try to translate some of that. Basically, it adopted the two techniques that we've been pushing. One is we're going to have pro-activation counters, and then the DRAM will raise alert if it needs time to perform mitigation. The reason why I have here an N, this is a hardware thing. It's a negative signal, so it's negation of the alert. Don't worry, it doesn't mean much. It's not that important. So for the first time, finally, we now have in DRAM all we need to stop Rowhammer. So I am not claiming here that now future DRAM is going to be Rowhammer free. And by the way, many DDR5 parts in the future are going to actually adopt PRAC, and they're going to come equipped with PRAC. And if you look at the trends in industry, in a few years, all DRAM is going to have PRAC inside of it. We're going to now count inside of it. I am not claiming DRAM is going to be Rowhammer free. All I'm claiming is that the DRAM, for the first time, it has the tools it needs to stop Rowhammer. If you want to understand how PRAC works, you can go read the DDR5 specification, which unfortunately is not free. And that's how JEDEC works. I cannot do much about that. But I have this little article on my website, which is free to read, that explains how DDR5 PRAC works. The title is DDR5 Spec Update has all it needs to end Rowhammer, will it? And it's free, obviously. So now, finally, the third chunk of my talk is to talk a little bit about how, in my opinion, Rowhammer remains far from being a solved problem. And in particular, I'm going to talk about the challenges with PRAC, with PRAC. And these slides are pretty dry, but I don't want to spend a lot of time on them. One problem is that PRAC, as any other Rowhammer defenses, only works if it's configured correctly. The specification in particular is silent on when the DRAM should raise alert, and is silent on how to configure the thresholds. Like, in other words, at which point the row becomes hot. And to configure these thresholds correctly, you need to actually use very conservative values that are going to perhaps eat away from your performance. And there is this typical trade-off that comes in security between performance and security. And unfortunately, if you look back at history, DRAM vendors do not have a very good track record on configuring their security mitigations to actually be conservative. In fact, quite the opposite. They're always very concerned about performance and not very concerned about security. So yes, you can implement PRAC inside of your part, but if you don't use conservative values, it's not going to eliminate. It's not going to stop Rowhammer. So that's one issue. The second problem challenge is that PRAC resets row counters. And ideally, you want to reset an aggressor rows counter only when all its potential victims are refreshed, right? You want to say, okay, so this counter now, all the disturbance is done this row, all the disturbance has done in the past, because I've refreshed the potential victim rows, has been undone. So I can now set my counter to 0 and start counting again. Unfortunately, the DRAM cannot guarantee that all the potential victims are refreshed atomically in one pass. There's no single point in time, and all of them are atomically. So the counters, by definition, will never be reset when all the victim rows are refreshed. They'll either be reset too early or too late. And that introduces a window of vulnerability. And it's not clear if there is a principled way to handle counter resets securely. Actually, I think there is a lot of work thinking about what the right way of handling counter resets is. The third problem I want to talk about is how rows span many DRAM chips. And let me give you an example. So this is a silly picture, but the whole of this picture is to convey. So when I actually talk about the DRAM row, that row handles all these chips on this side of the DIMM. So, it's the row actually, it's present through all these chips. PRAC works inside of a single chip. So there's a counter for each row in this chip. There's a counter for this row in this chip. There's a counter for this row in this chip. So every row has multiple counter values. And you might think because those counters increment every time a row is accessed, then they should be in sync. They should have the same value. Guess what? They're not in sync. So this row, this chip might actually basically will have a different counter value than this chip. So this chip might say, I need to go refresh the victim rows, whereas this guy might say, no, I'm not ready yet. It's fine. I don't have to do that. So there is a lot of inconsistency like that across the DRAM chips. And by the way, this working in some sense of tracking things is kind of redundant because the host doesn't read a single chip. It reads all of them. So that's a problem. It's kind of like an inelegant design. And one of the questions I would like to pose here is that should we redesign PRAC at the level of sub-row somehow? And how should that look like? And the last thing I want to talk about is that PRAC lacks a rigorous security analysis. And for instance, it turns out that the host can still, the CPU, the memory controller can still issue row activations during alerts. So although I've tried really, really, really hard at JDEC to basically argue that when alert is received, there shouldn't be any row activations because that's dangerous. There was a particular concern for a particular issue that they decided to actually introduce a small number of window where the host can still send up to a small number of row activations. I'm very concerned about that. Can those be used in some clever way to actually flip bits? I don't know. Something that is still far left to be seen. So we need PRAC to be configured correctly. Just to sum up, we need counter resets done properly. We need to handle out of shift counters. We need the principal security analysis. Alert is a very, very heavyweight mechanism, and there is a need to actually build something that's a lot more lightweight because we need a way for the DRAM to actually interrupt the memory controller. And the other idea I want to throw out there is that different rows, as we know actually, and people know this for a long time, are some rows are more resilient than others inside of the same chip to Rowhammer. So we should not have unique Rowhammer thresholds, but we should perhaps have per row Rowhammer thresholds. So to recap, the goal of my talk today was to convey three messages. And if there's something to take away is that there are these three messages that when it comes to Rowhammer and DRAM, the researchers have played a tremendous role in that they help kept industry honest. That if you want to actually solve problems when they come to security, you have to work together with industry and not opposing it. And it's a lot of frustration. Things are moving very slowly. It's not easy work. And us as researchers, we like to do fun work. This is not particularly fun, but that's how impact gets done. And although Rowhammer today, DRAM has all it needs to actually, all the tools it needs to stop, or mechanism it needs to stop Rowhammer, I don't believe Rowhammer is going to be stopped anytime soon. So we're going to continue to have this problem in industry. This work was made possible by the contributions of many colleagues and collaborators, and I've listed here everyone who worked closely with Project STEMA, although many others have made valuable occasional contributions along the way. Let me take a moment to acknowledge the people on this slide and briefly share their roles. Jeremy Kim and Minesh Patel were two exceptional summer interns who helped us launch the Project STEMA hardware lab. They're advised by owner Mutlu, and all three of them were instrumental in guiding us through DRAM internals and Rowhammer fundamentals. Lucian Kojokar joined Project STEMA as a postdoc, and he worked with us for 2 years. He's the original inventor of our fault injector and led much of the low-level hardware experimentation. Kevin Laughlin interned with Project STEMA twice, and he led Moesi Prime, which demonstrated how even commodity workloads, not just adversarial ones, can induce Rowhammer. And he also drove Silos, which explores how to enforce strong DRAM partitioning across cloud tenants. Kevin worked closely with his advisors, Boris Kasichki from the University of Washington, Yatin Manarkar from University of Michigan, and Dimitrios Karlatos from CMU, who are all fantastic collaborators. I also want to recognize Jonah Rosenblum, an undergraduate at the University of Michigan, who contributed to Silos. Lili Tsai also joined as an intern and explored how to detect speculative execution attacks by analyzing memory traces. Panopticon, our Rowhammer defense architecture for DRAM, was originally conceived by the brilliant Tansh Bennett. As I mentioned earlier, Microsoft's first-party silicon includes state-of-the-art Rowhammer defenses, and these were built by an extraordinary team of hardware engineers: Ishar Agarwal, Isaac Hernandez, and Will Remaklis. The architecture was co-designed with Daniel Berger and with Alec Wollman, and it was formally verified by Jay Lorch. I want to say that the verification that Jay did was confined to the algorithm that the defense actually uses, and not to the actual RTL Verilog code. Now, another key mission of Project STEMA is to assess Rowhammer risk across the fleet, and that work is led by Adam Grenzenbach right here, who is our hands, eyes, and ears on everything fleet-related. Finally, I would like to acknowledge Kushagra Vaid, who believed we could do impactful work in DRAM security even before we understood this space. Kushagra has been a true champion of bold technical ideas. At these early stages, we benefited a lot from Tim Kals, who encouraged us to go pursue this problem even when everyone else around us was telling us to stop because Rowhammer is not a problem. Tim is a DRAM veteran and made it clear to us that they're wrong and we should go do this. Dave Maltz funded our lab and made possible the acquisition of our bus analyzer, without which none of this work would exist. And I would like to acknowledge my manager, Victor Ball, who has offered constant support, tough questions, strategic guidance, and air cover throughout the 6 years of our work in Project STEMA. And of course, finally, Alec Wollman is my partner in crime. Alec's office is right next to mine, and every idea, thread, or spark we've ever had in Project STEMA has been shaped and sharpened by his insight. Thank you to all, and thank you for your listening to my talk. Again, this is the timeline for all the work we've done in Project STEMA. The title of my talk is 6 Years of Rowhammer. I hope you found it interesting. You can go to my website, and a lot of this work is linked off of my website. Thank you for your time, and please feel free to leave comments or send me email if you have any questions. Thank you.